Okay, so now I will give you a short introduction on statistical mechanics. So, so the early universe can be imagined as a hot gas of weakly interacting particles. Okay. Now, how can this gas be described? Okay, or how to characterize this gas uh, is the question. Now, it is actually not possible to characterize each and every particle of the gas. Instead, what we will do is we will characterize the entire gas, okay, statistically. So we will characterize the properties of gas statistically, and we will understand the entire gas instead of understanding each and every particle. Okay, so some key concepts I want to discuss about statistical mechanics. The first one is the distribution function. Okay, distribution function is a very important quantity in statistical mechanics. Okay, which is generally written as okay pt. So here we will be having a distribution function which will be a function of the momentum and temperature. It is a very cumbersome quantity actually, but here what will happen is since we are dealing with a universe which is homogeneous in nature, so the dependence of position will not be there. There is a dependence of momentum because and it will only depend on the magnitude of the momentum because we are dealing with the isotropic universe, so only the magnitude of the momentum is relevant to us and it is a function of temperature. Now today if we see the universe, there are only two kinds of particles, okay, which is either they are bosons or either they are fermions. Okay, now so we say that there are only two kinds of particles in the universe, which is bosons and fermions. We extrapolate this concept to very early universe also, and we say that in the early universe also there were only two kinds of particles, bosons and fermions. So we know the distribution function of bosons and fermions, which is written like this: 1 upon exponent of E of P, energy, uh, which is a function of momentum, okay, minus mu, okay, by T, okay, and plus or minus 1. Okay, so this is the form of the distribution function. This plus sign, if I take, it means that I am considering fermions, and if I take a negative sign, it means I am dealing with bosons. So this is the distribution function, and this is actually describing that how the particles are distributed among the energy levels. So this is what differentiates a fermion from a boson. Okay, so the distribution of particles in the energy levels. Now, the thing about statistical mechanics is that it acts as a bridge from microscopic physics, okay, to macroscopic physics. Okay, so what or microscopic to microscopic. Okay, so what we can do is we can understand the thing macroscopically, and based on the macroscopic properties we will understand what are the microscopic properties of the system. Okay, because it is not like if we take sun. Okay, so you cannot go inside the sun and find its microscopic properties. What we do is we say see the outer properties of the sun, and based on the properties of sun, macroscopic properties of the sun, we find the microscopic quantities. So this is how setmech works. So suppose if I want to find the number density of the particle. Okay, so number density of particle is nothing but summation over distribution function, okay, over p. Okay, so you have to take summation over all the distribution functions and you will get the number density, okay, of particles in the gas. Okay, so it is the number density of the particle inside the gas. So this is the thing. Now actually it is not convenient to take summation over all these things. It is convenient to convert this summation into an integration, but this is not a simple thing. Uh, so we will introduce the concept of density of states. So density of states is a very important, again, these are all very key concepts and very important concepts of statistical mechanics. So if I take a quantum mechanical phase space, okay, where this is the position and this is the momentum, and if a particle is traveling in this phase space, so how will the particle travel? Okay, in quantum mechanics, the particle cannot go smoothly from take a smooth line like this. Instead, what will happen is that due to the uncertainty relation, okay, there will be different states formed. So what will happen? That there will be a box. Okay, the particle can be anywhere in this box. You cannot say with certainty that where is the box, because we are having delta x into delta p. Okay, so this is the box with us. Okay, so particle will be going and there will be another box. Okay, so particle will be going from this box to this box, from this box to this box. And what is the size of the box? In 2 dimensions, the size of this box will be h square. Okay, and in 3 dimensions, the volume of the box will be h cube. Okay, so if we want to find that what are the total number of states, you can divide the entire volume with h cube. Okay, so you will know what is the total number of states. Okay, and if I divide this total number of states with volume, okay, so total number of states with volume, okay, it will give me the density of states, which is equal to 1 upon h cube. Okay, h I can write as 2 pi h bar, the whole cube. Okay, and in natural units we are taking h bar equal to 1, so it is 1 upon 2 pi cube. Okay, still the story is not finished. We have to also consider the degeneracy. Okay, because a particle can be degenerate, so accounting for that, the density of states, so if the degeneracy is equal to g, the density of states will be equal to g upon 2 pi cube. Okay, so this is a key concept, okay, which we have to understand, okay, regarding the density of states. Once we know the density of states, then it is possible for you to convert this summation into this integration. Okay, so now I can write, okay, the number density as number density n is equal to g upon 2 pi cube, okay, which is the density of states, integration of d cube p, okay, f of p t. Okay, so you can see it is p. Okay, so I have taken a summation over the three-dimension volume of the distribution function, and this will give me this. So since we are integrating with respect to p, the dependence of p will go and n will be only the function of temperature. Okay, so this is the number density of the particle inside the gas, and this is the form. Okay, so this is an important relation, okay, for the number density of the particles. Similarly, you can find the energy density, which I will call as rho. Okay, and this will be equal to g upon 2 pi cube integration of t cube p f of p t. Okay, so this is again a very important thing, and here also it will be a function of temperature only. Okay, since we are integrating with respect to t, and yeah, sorry, the main thing I forgot to keep here, into, since we are taking energy density, so it will be E of P. Okay, okay, so this is the energy. Okay, this is the energy. Okay, energy of the particle. okay, which is a function of momentum, and this is the distribution function, and this will give me the energy density. This is the number density. So these are the expressions of the number density, and this is the expression for energy density. Let us evaluate this thing. Okay. Now, what will happen is that depending on, okay, the particle, okay, each particle will have its own distribution function. Each species of particle will have its own distribution function. Okay, and since the distribution function changes, the number density of the particle will also change. The density of the particle will also change, and there will be also the pressure. Okay, so if you want to write the expression of pressure, you can also write the expression of pressure simultaneously. So this is the pressure. Okay, and the expression of pressure can be written like this: p square by 3 into E of P. Okay, so this is the expression for pressure exerted by the particle. Okay, so these are three very important expressions. The first is the number density, the second is the energy density, and the third is the pressure. Okay, so a different particle will have, okay, it's okay, since a particle, different species of particles will have their own mass, their own chemical potential, okay, and their own energy also. So based on this, you can say that this quantity will be different, and since the distribution function will change because it is a function of mass and this uh, chemical potential, so it will have a different n of t number density, it will have a different energy density, and it will have a different pressure. Okay, so for different species of particles, the number density, the energy density, and the pressure will be different, okay, because the distribution function changes. Okay, so species which are in actually thermal equilibrium, okay, early universe, when we are talking about this, we say that things are in thermal equilibrium. Okay, what I mean by thermal equilibrium is that particles are constantly interacting with each other, and when they are interacting with each other, they are also exchanging energy with each other. Okay, and since they are exchanging the energy, so the temperature of all the particles is same. Okay, so all particles share common temperature. Okay, when a particle goes out of thermal equilibrium, okay, it means that now it is not sharing the common temperature, it has gone beyond beyond equilibrium. Okay, so now it is no more in contact with the other particles, and it is now decoupled. Okay, so we will see what is the meaning of decoupling. Okay, it is a very important concept. So by thermal equilibrium I mean all particles are sharing common temperature. Okay, fine. For now, what we will do is, since we are dealing with very high temperatures, we are talking about right now we are dealing with very early universe which was in thermal equilibrium. At that point of time, okay, the temperature was much greater than the chemical potential. Okay, so it can be also proven for many particles. Okay, so what we will do is we will neglect for some time the chemical potential. Okay, now let us evaluate these quantities further. Okay, so if I want to see the expression of number density, so the number density is n of t g upon, okay, 2 pi q into dqp, okay, uh, and so just let me write it, okay, into f of pt. Okay, So this is the expression of the number density. Now what we can do is I can substitute the expression. Okay, let me take a spherical space. So I can write this d cube p is equal to 4 pi p square into dp. Okay, so this 4 pi and this will so what will happen is g upon 2 pi square integration from 0 to infinity dp, and so this p square factor is there, so p square upon exponential of, okay, now I am substituting the expression of this, so okay, and under root of p square plus m square, okay, divided by t plus or minus 1. Okay, so this is the expression. What I have done here is, so if we see the expression of free energy, sorry, the distribution function. So in this expression, what I have done is I have neglected mu. So I am having exponential of e of p by t plus or minus 1, and e of p, okay, can be written as under root of p square c square plus m square c to the power 4. In natural units, we take c equal to 1. So it is just under root of p square plus m square. Okay. So this is what I have done. So I have arrived at this expression, okay, which is the expression for number density. Now, similarly, you can write the expression for rho, okay, which is the energy density, and this will be equal to g upon 2 pi square. So it is 2 pi square like this. Integration from 0 to infinity, okay, dp p square, and here it will be p square plus m square divided by the same quantity exponent of under root of p square plus m square. So this is m divided by t plus or minus 1. Okay, so this is the expression for the energy density, and this is the expression for number density. Okay, we have neglected chemical potential for now. So in this expression, if I do some substitution of variables, so if I use a dimension variable which is x and define it as mass over temperature, and if I define another variable which is xi as momentum over temperature, then these things can be written like this. Okay, uh, n of t will be equal to g upon 2 pi square, okay, into t cube, okay, temperature cube, and there will be an integrand I plus of minus which will be a function of x, okay, and this value is I plus of minus x is equal to 0 to infinity t xi, okay, xi square exponent of under root of xi square plus x square and plus or minus 1. Similarly, for rho also we will be using the same variables, and we will be getting g upon 2 pi square t raised to 4, and here let me write the integral as j plus of minus x. This will be equal to 0 to infinity d xi to xi square under root of xi square plus x square under root of exponent of the root of xi square plus x square plus or minus 1. So this is the thing which we are having. Okay. So this integrals cannot be solved uh, analytically. We have to solve them numerically. So let me write directly the answer of this. So if we solve it for bosons, okay, then this integral, okay, will be equal to I minus of 0. Okay, so I'm taking negative sign this in this integral, which is for bosons. It will come out to be 2 xi of 3. Okay, so zeta. So this is the Riemannian zeta function, not xi. Okay, so these are all xi's. Okay, sorry for this. So this is the Riemannian zeta function. Okay, not this xi which I have written here, and this Riemannian zeta function of 3. Okay, so this is the value of this integral. You can solve it numerically, not analytically. And similarly, so this value of Riemannian zeta function xi of 3 is around 1 point, so it is 1.20205 and so on. There are few more digits. And if you find I plus of 0, which is for bosons, it will be equal to 3 by 4 times of I minus of 0, which means 3 by 4 into 2 times of Riemannian zeta function I of 3. Okay, so these are the expressions for, these are the answer for I plus and I minus. So we can write the expression for number density. So the number density is equal to xi of 3, which is the Riemannian zeta function, by pi square into gt cube into 1. Okay, if you multiply it with 1, then you will get the expression for bosons, and if you multiply this expression with 3 by 4, you will get the expression for fermions. So this is the value of number density of particles in the early universe. Okay, the other thing is the energy density. So I will just write the expression for energy density. The energy density rho will be equal to pi square by 30 g into t to the power 4 to 1, and if you multiply it with 1, you will get the expression for bosons, and if you multiply with 7 by 8, you will get the expression for fermions. Okay, so this is the expression for number density and the this thing. But one thing I want to say you, which I forgot, okay, is that these values of integrals are solved at I minus of 0. Why I minus of 0? It means that we are taking x tends to 0. In the limit x tends to 0, it means that, okay, we are taking, okay, m by t, okay, because x corresponds to m by t, and this tends to 0. This is only possible when t is very high. Okay, so we have taken that limit and then we have solved this integral. Okay, so we have considered that t is very high, so high that this x can be taken to be 0. Okay, or it tends to 0. Okay, so this is actually the limit in very early universe. Okay, in very early universe, this approximation is fine. So this approximation, okay, is actually known as the relativistic limit. Okay, so this expressions, okay, are in relativistic limit. Okay, so these expressions are derived in the relativistic limit. Okay, when the universe was very hot and at that point of time when things were in equilibrium. Okay, so it is the relativistic, derived in the relativistic limit. Okay, they were not applicable for all temperatures. Okay, if the temperature is very less, these expressions cannot be used. These are only used when the things are relativistic.